Before we talk about sampling and taking samples, we need to review what a sample is. A sample is denoted as little n and is a subset of an entire population, denoted as big N. Sampling from a population is important because typically we can't sample an entire population. Sampling also allows us to quantify the uncertainty in any estimates we make. Also, because we can only have information about the samples that we take, we cannot see the full sampling distribution or the distribution of the parameter estimate of interest from all possible samples. Because samples are taken from a population, random chance plays an important role in sampling. Sets of samples from the same population can be different, and estimates obtained from samples from the same population can differ by chance. Let's work with a hypothetical population of diamonds. There are diamonds of different colors and different sizes. There are a total, or big N, of 180 diamonds. Here is a hypothetical sample of 20 diamonds. If we take another sample of 20 diamonds, notice we have a different distribution of diamonds we sampled. If we take a third sample, the number and color of diamonds that we sampled changes again. There are two important things to remember about sampling. One, sampling is random, and the estimates obtained from sampling efforts vary and do not perfectly reflect true population parameters. Two, even though sampling is random, that does not mean that all the outcomes are equally probable. For example, we are more likely to collect gold diamonds because there are more gold diamonds in the population. And we will never collect large red diamonds because they are not present in this population. When dealing with samples, we should generate what's called a sampling distribution, the distribution of the parameter estimate of interest from the samples. We do this by taking a random sampling of size little n, calculate the parameter estimate, and then repeat the process many, many times. Now let's say we're interested in the proportion of large diamonds in the population. We can calculate the proportion of large diamonds in each sampling and then visualize it as a frequency plot. The y-axis is our number of replicates, our frequency of observations, and then on the x-axis you see the proportion estimated. The proportions range from less than 0.1 to 0.4, with the peak around 0.15. Since we know that the population parameter is 0.15, we can see that in general we get pretty close to the true population parameter with our estimate. If we do the same thing for gold diamonds, you can see that there is a larger range of estimated proportions.